Welcome back, Leo Lions. This is Mrs. Morgan with today's lesson over scale drawings. So scale drawings have to do with maps, maybe models, drawings of something that's in real life that's either really, really big or maybe it's really small. And then you make maybe a model, a drawing of it so that you can see a smaller version of it, or maybe larger if it's something very, very small. So I did a quick Google search. Here is an example of a blueprint of a house. And if you notice down here, it says scale ½ an inch equals 3 feet. So here is a picture of a bedroom with a kitchen. So it looks like maybe a 1-bedroom apartment. And what we would do then is for every ½ inch that we measure in this house, well, that represents 3 feet in real life. Now we can also see these on maps. So here's a map of New York. Down here in the bottom right-hand corner says 1 inch equals 1 mile. So if we measure 1 inch on that map in real life, that is 1 mile. So those are some examples of scales, scale maps, scale drawings. And we're going to apply that now to different scenarios with those models, drawings, maps. So if you were given a map that had a scale, the scale is always important. That is telling you the first measurement is always the map, the model, or the drawing, and then the 8 miles, the second number is always your real life distance. So this is saying that on this map, 1 centimeter equals 8 miles in real life. So how do we determine how many miles apart two cities are if they're 15 centimeters apart on the map? So you measure them, they're 15 centimeters. So here's a table showing you that 1 centimeter apart is 8 miles. So if we double those, 2 centimeters is 16 miles. 3 centimeters is 24 miles, so on, so on. We create this table and we get down after we list out to 15 centimeters, so that equals 120 miles in real life. So we used a table to figure that out. But as it says here, wow, that took a long time. There's got to be a faster way. So here's what we can do. We're going to create a proportion. So the given scale measurements, we're going to put as a fraction first. So the scale is 1 centimeter to 8 miles. This is what we were given in the problem. And most often we are given that. So we always put the smaller unit, so the smaller measurement, in the top. Like I said, almost always it's the first number. So 1 centimeter equals 8 miles in real life. The real life measurement always goes on bottom. Okay? Next, we're going to create another fraction and we're going to set them equal to each other. So here was our scale that we just took from up above. Now what we know were these cities were 15 centimeters apart. Notice centimeters was on the top. So the 15 centimeters that we were given also has to stay on the top. The bottom represented real life, so 8 represented miles. So we know when we solve for this x, it has to stay consistent, that we're solving for the number of miles apart that they are in real life. Now, once we set up this proportion, well, we have talked about in class, and here it's showing you the cross products. And this was erased, so there that should be an 8 on the bottom. So one diagonal is 8 times 15, the other diagonal is 1 times x, so 8 times 15 is 120. So x, we know that these two cities are 120 miles apart, okay? That whole example is done for you. Let's go to the backside and look at a couple more examples. Here we have example 1, a model of an airplane. So the model uses a scale of a ½ an inch is equal to 6 feet in real life. And this is very realistic. Unfortunately, it's not always 1 inch equals this or 1 centimeter is equal this. Sometimes we have fractions. So ½ an inch is 6 feet. The model, think about having a model airplane, that's the smaller of the two, that is 8.5 inches long. And what we're trying to find is the real life. If this model airplane was huge in person, then how many feet would the length of the actual airplane be? Okay, so we set up our proportion just like we did in the last problem. So the first fraction is always your scale. That's what we were given up here that I boxed in and we'll highlight 1/2 inch equals 6 feet. So 1/2 we changed to a decimal, 0.5 inches, and then that equals 6 feet. That's an easier number to work with when we multiply these. Now, we were given 8.5 inches is the model. So if you are unsure where to go, it's important to use those measurements, labels. So 0.5 inches is on the top, so 8.5 inches also has to go on the top. And what we're looking for is the real life measurement. The real life measurement is feet on the bottom, so we're going to be solving for x, and then we know it's going to be labeled feet. Okay? So now we want to use our cross products. This part is not done for us, so we need to keep going. We will multiply the two diagonals and set them equal to each other. So one diagonal is 0.5 times x, and then the other diagonal is 6 times 8.5. Okay, and you can use your calculator to multiply those, but once we get here, we have set up an equation. So 6 times 8.5, and I'm going to bring down that equal sign, equals 51, and then 0.5 times x we can't do. We don't know what x is, but our goal is to get x by itself on that side, so we have to get rid of that 0.5 by dividing by 0.5. And 51 divided by 0.5 is 102. Now again, you can use your calculator. I know that off the top of my head, but you could put in your calculator 51 divided by 0.5. Make sure you get the decimal in there. So what we just found was the actual length of the airplane, so make sure in the end we need to label and answer the question. So the airplane is 102 feet long. Now, would it make sense for our actual real-life airplane to be 102 inches? So that's why it always is important that we label our measurement in the end, okay? Next one. So now we have a model of a building. So here's a building over here. Think about having a model that you create. The scale is 1/4 of an inch is 12 feet. So this is going to be our first fraction in our proportion. Now, 1/4 we want to change to a decimal. 1/4, 1/4 is 0.25. Now I'm going to include those labels because that helps us then set up the second fraction. So 0.25 inches is equivalent to 12 feet in real life. Now, this example, it says if the actual, so the real life building is 984 feet. So in our second fraction, we need to put this number where it belongs, but we need to ask ourselves, should it go on the top or the bottom? And what are we solving for? What is the height of the model? So the model we put on the top. That was our inches. The actual real life was feet. That goes on the bottom. So 984 feet actually goes on the bottom, and you can always double check because those units have to match up and be the same. So the top, what we're actually finding is the model height of the building, and we're going to be finding that in inches, and we know those because again they match up on the top. Okay, so I created a proportion, and now we just need to solve our proportion. So we will use our cross products again. So 0.25, and it really doesn't matter. Maybe I'll keep it consistent with the last one. I'll keep the diagonal with the x in it first. So 12 times x is that one diagonal. The other diagonal is 0.25 times 984. So now we're at just solving an equation. So 0.25 times 984, we can do, that is 246. 12 times x we cannot do because we don't know what x is, but now we can solve for x. Get rid of the 12 by doing the opposite operation, divide by 12. So 246 divided by 12 is 20.5. 5. Again, we need to label our answer. So x, and we already put it in our proportion. This represents the height of the model. So the model is 20.5 or 20.5 inches tall. Okay? Last one, I want you to try and set up your proportion. I often start these examples by drawing a fraction equal to a fraction because we're always going to set up a proportion. All right, the scale always goes in the first fraction, and then you want to make sure that your units line up on the top and the bottom before you solve that proportion. Okay, pause, see if you can set up the proportion and solve this one. And then see if you're on the right track. So we got 1 centimeter is 8 feet. That is our scale. We've got a model of a cookie. So the cookie is 104 feet in diameter. That is the world's largest chocolate chip cookie. So that means the real life measurement. So we're trying to find the diameter of the model. Okay. So first of all, let's put our scale in the first fraction. 1 centimeter is 8 feet in real life. We put centimeters on top, so we need to keep centimeters on top in the second fraction. We put feet on the bottom, so we have to keep feet on the bottom as well. So the next fraction, we need to decide what were we given. Were we given the real life or were we given the model? In this case, feet, 104 feet, that was the real life diameter of the cookie. All right, and we are solving for the diameter of the model. So there is our proportion. Now we will use our cross products. Again, I'm going to keep it consistent with the 8 times x, the x first, and that equals 1 times 104. So 1 times anything is itself. And then to solve for x, we need to undo the 8 times and divide both sides by 8. So x is 13. And again, we need to label. This is the model of the cookie. So the diameter is 13 centimeters on the model. All right. So those are our examples for our notes. The next page then is going to be a homework assignment, and we're going to talk about a couple of these in class, but I want to point out that this scale right here you are using for numbers 1 and 2. So both of these examples, you're using the same scale. Okay, we're going to talk about 3 and 4 in class, and then that should help you with the rest of the assignment.